Okay, so as the part of this lecture or this DGD session was covered in the previous third DGD session, and some of you asked me to not go ahead of the syllabus, and there was a confusion there. So based on that, I'm not covering your future lectures. I'll be covering what was taught yesterday. I think it was electric current and resistances, not circuits. Am I correct? Perfect. So I'll be covering resistances and electric current. Also, part of the questions what I'll be dealing today was covered in third DGT session. We'll go through them step by step, so they will make more sense now as compared to before. Perfect. I'll share my screen. Everybody can see my screen, right? Thank you. So again, welcome to the fifth DGT session. In this session, we'll be covering electric current and resistances. As part of it was covered in third DGT session, but I'm going to repeat it. If you have any doubt, you can open your mic at any time and ask me a question. Okay, let's go ahead. Start. So the first question says that a copper wire has a circular cross section with radius of 1.25 millimeters. If the wire carries a current of 3.7 amperes, find the drift speed of the electron. We have to find the drift velocity of the electron. So again, we see what's given in the question. They gave us radii, they gave us current. They gave us current. Sorry for that. Yeah, they gave us current. So we have to find the drift velocity. So we use what is given in the question, and we use the formula here. I'm not going to write it again. This comes from the formula here, and this originates from this equation. Okay. We use it's a direct application of the formula. Area is given by pi r squared. R is given directly, and you apply. Part B of the equation is, all other things being equal, what happens to the drift speed in wires made of metal having a larger number of conduction electrons per atom than copper? So as you see here, Vd is inversely proportional to Ne. So if the conduction electrons are larger, then V will decrease. Right? Why did I write? Yeah, so it should decrease. So if Ne increases, drift velocity will decrease. And you guys are familiar what is drift velocity. Am I correct? Just give me a hint that you guys know that you guys are familiar with the concept. Perfect. So I think this question was straightforward. I'll move on to the next question. If no doubt, I'll move on. Say yes or something. Thank you. I have no idea how, like, so I just need a stimulus from you guys that, yeah, move on to the next question. Okay, so second question, it says that figure, we have given a conical figure which represents a cross section of a conductor having a non-uniform diameter, and it's carrying a current. Again, we see what's given, carrying a current I, given some value 5 amperes, 5 amperes, and radius of cross section is given, R1 is given as well. What is the magnitude of the current across A1? And another information is given in the first part, that radius R2 at A2 is larger than the radius at R1. But again, this part that is given has nothing to do with the first part of the question. It is relevant for the next parts. Current density is given by J. Current density is given as I by A, current per unit area, and you know the radius as it's given in the question here. Let me write it by R1, and current is given. You apply the formula directly. Is the current at A2 larger, smaller, or the same? The thing is, current remains same. Current density is different because that is dependent on per unit area, but current is same. Current is independent of area, hence remains same. Let's move on to the next part. Is the current density at A2 larger, smaller, or the same? So you know current is I by A. If area is larger, J is smaller. That means J2 is less than J1, as you see that here. Let's move on to the D part. D part say what, specify the radius. You use the equation. It's given that A2 is 4 times A1. That's what you use. Oh, I wrote this here as well. Yeah. So I just equate that to find the radius. Okay. Now the current is same. We established that in the second part of the question, and the current density is Four. Does this make sense? Any doubts? Thank you. I'll move on to the next one. This says an electric current and carry varies with time. So now electric current is a function of time given. Whenever you see something with a function of time, then you should assume always, when it's given in the problem, that there is a derivative and integral involved in the question. That's a trick. So whenever something varies with time, that means the continuous variable. That means you have to do some sort of derivation, like speaking in terms of mathematically speaking, that there is integral or derivative involved. So you always prepare for that. My sign is not good. Yeah. What is the total charge? To find total charge, from t equals to 0 to t equals to 1 by 60 seconds from a given point. So if you remember, this is the equation. Current through an infinitesimal charge dq at a given moment dt is given as dq by dt. Correct? Then I can use dq as I dt, total charge passing through from 0 to 1 by 60 seconds. Now substituting the values, I get this. So total charge flowing this moment will be given as Is this okay? Anybody has any sort of doubt? You did it the same way you practiced before. That's very good. And this is another reason I didn't send you the PDF of the questions I'm going to be covering, because part of this was covered in the previous TGD session. That's why. So now by the next session I'll be at the point what will be covered by your prof in the next 2 lectures. So I'm not moving ahead. I'll be at the same speed. Okay. Next question, if there's no doubt, I'll move ahead. Next question is a bit conceptual kind of thing. It's related to the real life. I thought it's a good thing to give you an idea. So there is something called plethysmographs. These plethysmographs are used to monitor your blood pressure and specifically monitor the change in volume of your internal organ in the body. Okay, so I'll read the question. These graphs are devices used for measuring changes in the volume of internal organs or limbs in the human body. In one form of this device, a rubber capillary tube. Now this is the question. Rubber capillary tube with an inside diameter. Again, let's say what's given. Given radius, and it is filled with mercury at temperature. The resistance of the mercury is measured with the aid of electrodes sealed into the ends of the tube. So resistance is measured by some sensor in the real life. If 100 centimeter of the tube is wound in a helix around patient's arm, the blood flow during a heartbeat causes the arm to expand, stretching the length of the tube by some centimeters. From this observation, and assuming cylindrical symmetry, that cylindrical symmetry means that it's a wire, you can find the change in volume of the arm, which gives an indication of the blood flow. That's how the device works. Take the resistivity of the mercury is given, and another hint is whenever in any question hint is given, that means you have to use this hint. Never ignore any hint. That's how you get to know how you do the problem. Okay, so the fraction by which the cross-sectional area of the mercury column decreases is the fraction by which the length increases. Hence, if the area decreases, length increases. The product of area and length is volume, therefore volume remains unchanged. So very important point is given as A decreases, L increases, therefore volume remains unchanged. Let's solve first part. Calculate the resistance of the mercury. A resistance is given by, you know this formula, rho is the resistivity, right? Length is given, area is given. So length is given as 100 centimeters here, area is given, radius is given here. You solve it. Is it correct? I mean, you get it? I'll move on to the next part then. Okay, say something here. Perfect. So let's move on to the B part. It says calculate the fractional changes resistance during the heartbeat. So let's read the question again. What happens during the heartbeat? So from this observation, sorry, if 100 centimeter, here, if 100 centimeter of the tube is wound in a helix around a patient arm, the blood flow during a heartbeat causes the arm to expand, stretching the length of the tube by. So during the heartbeat, length expands. That means your resistance changes, not resistivity, your resistance. Okay, then you have to find the fraction change in resistance during the heartbeat, how much it changes due to your length changes. As you think of it as when the temperature increases, your length increases of the total wire and your resistance changes. So your question is asking how much is your fractional change in the resistance. That is delta R by R, that is RF minus RI by RI, or RF by RI minus 1. That's what your question is asking you to solve. Okay, how do you do that? So you need to find RF, right? Let's see, this is where, how to find RF, this is where the given comes in. Volume remains constant, therefore AF, final area into final length, that is given as LF plus LI plus 0.0365. Okay, you change it into meters into 10 to the power minus 2. Use SI units for all. Equals to AI into LI. That should be smaller. Yeah. So AF can be written as. Now you must be wondering why I'm doing this, because I need to find the final resistance. That's how I'm going to find RF, and RF is given as rho LF. F stands for final, I stands for initial, by AF, and I'm using AF from here. I'll get rho LF AI Li into LF. Does this make sense, everybody? No, you can ask me questions if you have some problem. So I'm just using the equation rho L by, where rho is the resistivity, L is the length, and area, A is the area of the cross section. And because the question says that its final, the volume remains same, I'm exploiting the fact to find the final resistance. In fact, this is how you do in every question, which says there is a temperature change and the length changes due to the temperature. You find the final resistance if the volume remains constant. Okay, otherwise there's other ways. You use the equation rho equals to rho naught 1 plus alpha t by t minus t naught. That's the equation we're going to use in the next question. Okay, if it makes sense, then I'm going to just divide by Ri, left side of the equation, and also the right side equation, and square f by AI Li into Ri, and substituting for Ri as rho Li by AI, I'll get L square F by L square I. Call it equation 1. Substituting in equation 1, we get substituting in equation 1, we get delta R by R as LF Li whole square minus 1. Let's you substitute the values and you get the answer. Is it okay? Any questions? It's okay for other people as well. Perfect. Thank you. I'll move on to the next question, if it's okay. Yeah, let me go ahead. Sorry, there was some notification on my device. Let's move on to the next question. Again, this was covered in the previous DGT, but I'm going to solve it again because I think it's an important question. Suppose you wish somebody gave you a job to fabricate a uniform wire with a mass m given. That's why I always break up questions. Something is given: mass density, that mass per unit volume, and resistivity. That's given and the wire has a resistance R. What is the length should be used? So you have to find the length in terms of the given wire density, that is mass density, resistivity, and the rate resistance. You know that what is R rho, come on, rho L by A. This equation seems to be working everywhere, right? So, and what is, we have to find L here. We have rho, we have R, we don't have A, right? What is A? V by L. Volume of area of cross section into length is the total volume, right? Now you know that using the given, using the given mass is given as rho m into V, which can be written as rho m into A into L. From here I can find A. Therefore A is given as m by rho m into L. Therefore R can be written as rho L by m divided by rho m into L. Therefore L square is given as m r rho m. Therefore L can be written as m r rho m. You see, I'm just using what's given in the equation, or given in the question beforehand. It says rho m is given, I'm using A from rho m. So the trick was just to find A from the given quantity right here. Is it, did you guys get it? I'll move on to the second part if you guys have no doubt. Perfect, thank you. And B part says find the diameter of the wire. Again, you have to find the diameter. What is the volume? By di square by 4 into L, right? Length. So it's pi r square h, right? The volume of a cylinder. Then R is d by 2. That means pi di square by 4 into L. L is the length of the wire that you solved here in the first part, right? And what is volume? Volume is given as, from here we can find volume. From here you can find volume. Therefore m by rho m pi by 4 di square into L, and from here you can find di as 4m by rho of m into pi into L, and you substitute for L, you get your answer. Is it correct? Right? If it's okay, I'll move on to the next part. Any questions here till here? Perfect. Let's move on to the next question. At what temperature will silver have a resistivity that is 2 times the resistivity of tungsten at room temperature? Again, given in the question, whenever you will be solving in the exam, if this comes, the question will give you the resistivity of silver. So rho silver, it will be given some value in the question, given rho tungsten, some value will be given in your question, given room temperature T0 is 20 degrees Celsius. So the question asks, at what temperature silver have a resistivity that is 2 times the resistivity of tungsten? So as if you know, rho is given as rho naught, I'm talking about tungsten here, tungsten 1 plus alpha. So this is the equation for variation of resistivity with temperature. So if you know what happens when you increase the temperature of a wire or a conductor, the resistivity increases because electrons collide more because of the heat, because of the extra energy they have due to the temperature. The relaxation time decreases between the collision. I think so. If you have covered resistivity, you have seen this in the class. We're waiting for Billy's comment. He's typing. Okay, I'm giving you the picture how it happens physically. Okay, let's say you're heating a wire, then the electrons have more energy. They have more energy. That means they have more kinetic energy. That means they travel faster and they travel in haphazard motion. That means they collide more. If they collide more, the resistance increases. They don't follow the same path. That's why resistivity is directly proportional to temperature. As resistivity increases, temperature as resistance. So temperature increases, resistivity increases, and then resistance increases. This is how you physically picture it, that resistivity and resistance increases with the temperature. This is true for normal ohmic conductors. If you go superconductivity, is different. There's something called T3/2 law, but I'm not going there. So does that make sense? I'll move on. I'll continue the question. Somebody's typing. This is why gold is used because gold has a low temperature coefficient. Water computer increase the temperature, the gold resistivity doesn't increase as fast as silver or copper. Yeah, these are different facts. Silver and gold has the lowest resistivity, and that's why they're used as a conductor in your expensive devices and almost in all electronic devices. And that's why if you it's okay, you can share the information, and that's a good information you're sharing. Again, add on to it that you see whenever, let's say, Apple people ask you to recycle the iPhone, they just not throw it away or dump it somewhere environmental friendly. They just take every part of it. They take the gold out of it. Gold is the biggest thing they collect from electronic devices, from your garbage. So if you're giving a TV or, let's say, an electronic device, first thing they take out is the gold out of it. All the electronic devices has gold. So This is the fact. Again. Yeah, and it's also given in the book, so you can read it. I read that. And at what temperature will silver have a resistivity that is 2 times the resistivity of tungsten? Okay. So let me write it. Let's say silver. Oh, sorry. I have to find. I just equate this equation to 2 times rho tungsten. That is rho naught silver plus alpha T minus T naught. From here I can find 2 rho tungsten by 2 rho naught silver is equals to 1 plus alpha T minus T naught. That is equals to T minus T naught 2 rho tungsten by rho naught silver minus 1 by alpha, and T is 20 degrees plus, substituting the value of T naught, so that's the answer. Do you have any? I'll read it again. So I wrote an equation how resistivity of silver changes with temperature, and it asks, the question asks, at what temperature will silver have a resistivity that is 2 times the tungsten, and that's what I'm writing here. Let's say that temperature is T. Using the above equation, I'm substituting that, and then I'm solving for T. That's what I get it in the end for T. Is it okay? You guys get it? Cool. I think this is the last problem of today. I think we are gonna wrap this session earlier. So that's the 7th question for today. Yeah, it's just the concept was I went through it like I think little fast or something, or the questions were not that difficult. Something, I don't know. Given Anthony's typing, I'll move on to the next question before he says something. Yeah. Okay. The question says, let me increase it to size. Yeah. 210 watts of heating coil. Again, this is a real life based question designed to operate 110 volts. Is made of nichrome wire. That is very rare to find though. So we're given, that's what you always do, right? Given the voltage that it operates is 110 volts. A wire radius is given to be 0.54 to 10 to the power minus 3 by 2. and rho alpha is given for nichrome. Power is also given as 210 watt. Assuming the resistivity, the question asks, the first part, assuming the resistivity of the nichrome remains constant at its 20 degrees Celsius value, find the length of the wire used. Right. So again, our favorite equation is rho L by A. We have to find A, L. We have A, we have rho, do we have R? How do you find it? We don't have R, right? It's not given in the question, but power is given, voltage is given. So power, what is this? Power is given as V into I, right? And V is also equals to IR by Ohm's law. Then I can be written as V by R. Doesn't matter, I'm using delta V for the power, the voltage designation in your households. So that's how they say. And yeah, also Ohm's law is delta V. So just being accurate here. Where therefore you can find R as delta V square by P. Right? Now you can substitute it back to get this. Substituting back, I'm getting L as A into delta V square by P divided by rho. That's the first part. Did you guys get it? Any problem in any equation or something? Good. Perfect. Let's move on to the part B. Part B says, now consider the variation of resistivity with temperature. Again, you know our favorite equation, not so favorite though, but yeah, is this. And it says what power is delivered to the coil when it is warm to 1200 degrees Celsius. Now you know, because if you change the temperature, that means your resistance changes. That means if you have to calculate power that is given by this equation, you have V, but you don't have R. You need to find R, and R changes due to this equation, right? So how do you do that? You just apply the formula. You can write it as rho naught. You have given alpha, you have given as 200 degrees Celsius, 1200 degrees Celsius. T naught is given in the equation. Just a minute. Yeah, 20 degrees. It's right here. Minus 20 degrees. You use that. You find rho from R is given as rho L by A. You find R and you substitute it back to the equation. Let's call it RF delta V square. Let's call it RF rho F delta V square by rho F L by A. Is any questions here? can ask me any doubt if you guys have. Okay, so the question asked me that. I did that. You have calculated the length here. You substituted length here. You have area. You calculated rho f here, and every variable is known now, so you can find the power. Okay, so I'm gonna conclude today's session. Before concluding, let's conclude first. So today I covered electric current and resistances. I covered the drift velocity part of it. I covered the variation of resistance with area and length. I covered the current that are varying with time, that is continuous current distributions. Then I covered the variation of resistivity with temperature and the variation of current with power. Wire carrying power, certain power, and we covered that part of the syllabus as well. So that is it for today. And if you guys have any questions related to your lecture, what Prof covered it for you, you can ask me right now. We have some time left. If you want to tell me something about your midterm, how it was good, was DGD helpful, you can say that for as well. I mean, anything, we have time. So something you want me to change some ways, like DGD sessions, so that it's covering your question exams well, something like that, some suggestions.